Right, we now have another talk on a bit of maths, which is Fractals on the Pie by Sean Martin. I will give you a green.
Yep.
That 5 minutes to go.
Orange and red, isn't it?
Orange and red.
Yep.
Yeah. So.
Thank you. Yep. Oh, good afternoon. There aren't many children. Can I start by asking who's familiar with fractals? Have some of you? Oh, quite a few. So have you written programs that generate fractals in the past? A long time ago, yeah. Probably late 80s, early 90s, maybe? No, a little later? Okay, so this is a very kind of short talk. I had to pitch it on the assumption that perhaps people weren't so familiar with fractals, so if you're more expert, then forgive me for that. So I looked around a couple of introductory resources. A common theme was this kind of statement: as a natural phenomena or a mathematical set that exhibits a repeating pattern that displays at scale, and they call this property self-similarity. So here's some examples from the natural world. I think, for example, the galaxy, if you zoom in, you can expect to see some kind of similar patterns at greater resolution. And probably those of you who've written such programs will recognize that particular beast as a Mandelbrot set. So science, maths, and art, some kind of overlap between those spaces. The maths background is pretty heavy duty. I won't go into that. This chap, Mandelbrot, wrote an article, was working in that field, published an article in 1980, and it was fairly quiet for a few years until Scientific American picked it up. And then, the place I was working at the time, an awful lot of computers were working overnight to produce Mandelbrot pictures, static Mandelbrot pictures. So you'll see some that aren't static later on. Right-hand side, the basic method, as you may remember, is that a new value in a series is an old value squared plus some constant. It's a repeating kind of pattern. Mandelbrot is not the only form of fractal, but it's the one that got to be most well known. So, where's my mouse gone? There's an example. I took those from a reference book on fractals. This one I happen to particularly like. And I can zoom into that, and I can pan across the image. And what's happening is that a server is calculating those images on the fly, and the viewer is doing a zoom and pan delivery of those images. That was with a cache. This one is without a cache. And what you'll see now is it progressively increasing the resolution. And if you can look carefully, you still might see it coming into focus in various parts. And I'll explain how that is happening. So the viewer works as follows, that here is a timeline plot of the HTTP requests that the viewer is making back to the server. First of all, the top line is a file called info.json, essentially an XML file that tells the viewer what the image dimensions are. And then the viewer works out what it would like to ask the server for. And you'll see there essentially largely a sequence of image requests to a server, which then calculates them on the fly. Those particular image requests are those. There are 6 progressive requests for images which are of the complete image, and then a series of 4 which are for parts of the image but at a higher resolution. When I zoomed in, you will see obviously it zooming in, and in terms of the behavior that it is happening then, what happens when you request to zoom in, it magnifies the images that it already has and presents them at apparently higher resolution, or increases the screen area, while it asks the server for images at higher resolution. When they arrive, it superimposes them, and it gives the illusion then of being able to fly around. But in fact, it's by a series of static images. So it took that series of, that's the sequence of zoomed-in image requests, which resulted in this set of images being requested from the server. So you'll see a group of 6 on the left at 1 resolution, then a set of 12 on the right at a slightly higher resolution. And the viewer took that set of images and it produced that as the composite image that it was displayed. So it holds in memory in the browser a set of static images and then it superimposes them in order to produce this kind of dynamic image. The viewer is based on some fairly recent work which has really come out of the library community called IIF, International Image Interoperability Framework. I was working at the British Library until earlier in the year, and we were closely involved in this alongside a number of other national libraries and universities, essentially for viewing digitized manuscript or book kind of material. So here is an example of the technology for which I derived that. This is a classic manuscript held by the British Library. If I zoom in onto this blue background, it looks kind of fuzzy, arbitrary shapes, but when you zoom in, you may now start to see angel figures in the background of the image. So this is a manuscript. When you digitize an image, it's typically at most 8,000 by 10,000 pixels. The fractal images that we've just been looking at are 8 million pixels wide, 8 million pixels high. So the level you can zoom in is an awful lot more than you can with a digitized image. So what the IIF initiative has done is to work out a HTTP-based protocol for being able to request images at arbitrary parts of the complete image and at arbitrary resolutions of the complete image. So a typical IIF architecture has a browser running JavaScript and displaying JPEG images. It talks from the browser to a server with the IIF interface as now a standard request protocol. In front of a web server, there's a cache server. Then the web server which takes the IIF request and it works out how to control a piece of software that will extract parts of the image on demand. And that generically is an image extractor. And this now gets a bit over-specialized. Software that almost everyone uses happens to be called Kakadu, and it uses JPEG 2000 master images. Not JPEG, these are JPEG 2000 is quite different. It's the only file format that can very efficiently support extractions of portions of the image and sufficiently fast that you can do it on the fly. So basically, there's the IIF architecture there. What I've done is to take that architecture so that the browser and all of the other parts are the same, as far as down to the level of the image extractor. And I replaced it with a fractal generator. And as I said earlier, the sizes of the virtual images are extremely large. So what the generator does is it says, I have an image for you which happens to be 8 million by 8 million rather than 10,000 by 10,000. And the rest of the stack works exactly the same. It's just it's working with much larger numbers. I took a free cloud server from Amazon. I deliberately chose Debian, and I got that running on an Amazon server and also running on a Pi as it's running Debian as well. What I found was that the Pi is not exactly fast, so I had to tune the web server a bit in order to get it to stop timing out, but that was, in the end, that was quite successful, and I'll show you that presently. So those of you who have written this kind of thing before will probably now start to remember one or two things if it was some while ago. So for each pixel, and hence for each row, we assign an X value. For each column, we assign a Y value. We use complex arithmetic. We start with a value of 0, and then we loop replacing z with z squared plus c until some condition is met, and otherwise you loop back, and then you get a value which is typically between 0 and 255. That was part one. Part two is how to assign colours to the various parts. And I've remembered now that I've omitted one bit of the fractal display that I'll go back to, because it's reliant on how you generate the colours. And the last bit was how to generate a JPEG. Let me just go back to the bit that I inadvertently left out. So that's the pattern that I showed you before. I found this good reference book, and it had quite a good tutorial. The pattern at the top is the complete set, as you may remember. The one here happens to be taken as an expansion from this part of the whole one. So if I take that part there and zoom in, then you see that pattern, which is one of the different examples on that page, which is that one. And this one above is from the top, just off the top of the main part of the figure. And you'll see here a recurrence of that particular pattern. So as you move in, and this issue about self kind of similarity, as you move into more depth, you see parts of the pattern reoccurring. So the tutorial guide, here for example, at this part of the main image, you would find this example. I'll just go straight to that. And if you zoom into that part, you see that figure that I'd been showing you before. And if on that one, you zoom into the top part, you see the later parts of the figure, and you now see a recurrence of that kind of seahorse tail and various things, which in turn would repeat as you go into more and more depth. So you've got this pattern which is similar at various levels of magnification, and that was the tutorial guide for that. The one part I wanted to just highlight was this, which was here you'll see bands of green and blue. And I'll explain how those were generated alongside these kind of slightly fiery colours around the edge of the black. So here, for example, was the means by which I took a value between 0 and 255, and then to generate 3-colour red, green, and blue code. So you'll see there's a little test here that if it was even, then show predominantly green. If it was odd, then show predominantly blue. And that's how I got the green and blue patterns. And then the red colours were coming out through some of the other tests there. So it's simply an assignment through to the colour space from that first initial value. And one can play around with those colour assignments. And they're actually not part of the core piece of code for that at all. So I coded it all in C. The core loop is there. I was counting quite carefully how many flops, floating point operations there were. Within that core loop, there's 8. But we repeat and go around that lots and lots of times. And basically, it causes the Raspberry to go flat out for quite a while, as we'll see in a moment. So maybe a philosophical question. Many people I've asked, well, how is it that 25 lines of code like that can produce patterns like these? And I've not found anyone who can tell me the answer other than, at the end of the day, well, it looks pretty. That's why I think there's this kind of curious overlap between maths and art here. So in the last lap or two here, so I explained I have a technology stack running on an Amazon server with the same stack running on a Pi. So this is the Amazon server running without a cache, but you can still see the sequence of images coming in as it calculates them and delivers them. If I take the Pi server without a cache and you look at it quite carefully, well, you'll see that it's quite slow to start with. It's pretty coarse, it gets better, but actually if you look in detail, you'll see the effects of the images coming in for really quite a long while. So if I repeat that, again, pi, but this time with a cache, it's very hard to tell the difference between it and the Amazon server. So on the initial load, the cache really speeds up the initial load. If you go and zoom in, actually it's still calculating stuff that isn't in the cache. So, but the fact of the zoom, it shows existing images at higher resolution. Actually, quite often you don't notice that that's the case. So here's the transfer sequence from that Amazon server for an initial load, and it's delivering most of those images in just over a second. The corresponding case, when I run from my Raspberry Pi at home, it's taking over 8 seconds to do that. So it's order of 8 to 10 times slower than this free server I have from Amazon. The IIF initiative will continue, and one of the things I'll be doing is assisting with putting demos together for that, and we'll put up a Fractal demo of that. It will be in the latter part of this year, and that will be at demos.iif.io. Thank you.